I'm pleased to have Botong Wang, who will be speaking about Chow Quotients of Toric and Schubert Varieties by C***.
Thank you. I want to thank the organizers for the opportunity to speak here, and it has been a wonderful conference and also a wonderful special year. And I'm really happy to report something, some joint work with or joint project with Mateusz and Leonid. Mateusz is here. Leonid visited here last fall. And this whole project started since the special year. If there's no special year, there's not. None of what I'm gonna tell you will be happening. I mean, they won't exist. So I never met any of my collaborators here before the special year, and I don't even know what Chow quotient is before the special year. So I mean, I know Toric and Schubert varieties are, and that's like. Okay. One thing I learned from Mateusz is you can do nice talk on blackboard. So let me tell you the motivation. This is the history. So this was briefly mentioned in the morning. There's this theory of poset, and the combinatorics of a poset is you can attach this notion of Casaluci polynomial and kernel to a poset. Let me give you like 2 minutes introduction to this. So the history is Casaluci introduced the famous Casaluci polynomial for Coxeter group. If you have Coxeter group, you have 2 elements that's comparable. Okay, if it's not comparable, you get 0. If it's comparable, you can define a polynomial z coefficient. Okay, t will always be my variable. Z coefficient, and they defined it with motivation in representation theory, but the way I view it, or is maybe better for this conference, is algebraic geometrically it measures the singularity of the Schubert variety. It measures the failure of local Polynomial duality. And if you like more of a combinatorial point of view, it measures in some sense the failure. Okay, this is a little bit vague. Is the failure of the lower Bruhat. Okay, let me capitalize the lower Bruhat intervals in the Coxeter group being palindromic. If everything is smooth, all the Schubert variety have Polynomial duality, then that will tell you all the lower Bruhat intervals has to be palindromic. And this in general is not true because the Schubert variety has singularity, and singularity is reflected by the Casaluci. And then Stanley realized that you can kind of take the idea of Casaluci polynomial and generalize it, at least to polytopes, and to more generally this abstract notion of Casaluci polynomial for a poset. So he defined a key part of definition is the kernel of a poset. So in this case, it will be the R polynomial. Okay, I'll tell you more later in my second slide. So there is the notion of kernel of a poset. So let me just tell you this one. I can tell you a formula. So if I'm poset for us is always graded. If I have a graded poset and the kernel assign every pair of comparable elements a polynomial. The polynomial being a kernel simply means, okay, the definition is if UU on like UU is pair, if the pair is the same, you just assign 1. If the pair, is V strictly bigger than U, you require this relation. So you take the kernel polynomial and you of the first interval. And for the second, so you add an element in between and you sum over W. So U and V are fixed. W is varying. You take the kernel of the first one and the reverse of the kernel of the second one. So expect this is a polynomial of degree, which is the rank of V minus rank of W. And you revert, meaning like you just write it as polynomial and change the coefficient of degree 0 to the top degree. And the top degree is rank V minus rank W. And you produce a new polynomial. This is called reverse polynomial, and you just require the summing. I hope I didn't make it. Where's the local expert? It's good. Okay. And then, like next slide. Big one. Once you have a kernel, Stanley says there is a unique way. Okay, Stanley only consider right causality polynomial. I believe you can associate a right kernel. Here I will not tell you the formula. The idea is K uniquely determine a causality polynomial, and now it's called K causality Stanley polynomial. And I guess Brandy took his idea a little bit one step further, so he can also define a left KLS polynomial, and kernel determines each of them, and each of them also go back determines the kernel. So it's really like you have a triangle, and if you know each of them, you know everything. Okay, and now there is some more recent development. This is not exactly the one mentioned in Eric's talk. It's the follow-up paper. It's more recent. That paper also occurred during the last part, the end of last year. So it's during the special year. So Louis, Mather, Vecchi studied this notion of a Chow polynomial, or they introduced this notion of Chow polynomial for general poset with a kernel. So what they said is, if you have a poset with a kernel satisfying this condition, they have some formulas to produce a new polynomial. Magically, if K satisfies the kernel condition, then this polynomial will be palindromic. Of degree, the interesting part is of degree is not what you usually expect, is like V, the rank of V minus rank U, but it's you subtract by 1. And okay, so this is when they are different, they are same, it's just okay. Okay, so what's really happening behind all this like definition and combinatorics? There are really like geometry behind almost everything. So if I start with the polytope, combinatorics have polytope, geometry have a toric variety. If your polytope is rational, by XP I mean the toric variety of the normal fan. So it's the normal fan of the polytope. Okay, again, polytope for us always mean a convex polytope. And then this case, the kernel function is always nice. It's always t minus 1 to a power. The power is the difference of the rank. So face poset a polytope. Okay, I hope you know what this means. It's just the faces, and there's the inclusion is and it's also graded by the dimension. So here the rank function is just dimension. And geometrically, this is the Poincare polynomial of a torus. So you should I think of the torus as like a normal slice. So you have two faces. It's a normal slice of the small face against the bigger face, something. Okay, and okay, here we should double check with Louis. So the left KSL polynomial is 1. That's not correct.
So the right KLS is the toric G polynomial of the polytope, and the left is the toric G polynomial of the polar dual of the polytope.
Okay, so thanks. So this is G. This is the G polynomial. You are telling me the left is the G.
Yeah. So one is the one corresponding to P, and the other of the polar dual of P.
Okay, of P and G. Okay. Some polar dual of P.
Or the other way.
Oh, the other way. Okay, so maybe easier now to. Okay, but they basically measure. Okay, so I'm not sure about the polar dual, but they basically measure, or at least one of them measures the singularity of the toric variety. And here, to be precise, I mean like the local. Okay, here I didn't want to be super precise. It's like the local intersection cohomology group of the toric. And then, so far everything here we cannot understand what they are. But for Chow polynomial, it's not clear. And Louis has some partial answer if you are curious. So there's not a very, as I understand.
Yeah. We know what goes there. So that's the H polynomial of the barycentric subdivision of the polytope.
For every polytope.
For every polytope.
Okay. Yeah. So there is an answer. So, okay, there's no question mark, just ask Luis, you know.
You designated him an expert too.
And then for Coxeter group, the combinatorics is Coxeter group, the algebraic geometry is the Schubert variety or the flag variety with the Schubert cell decomposition, however you want to say this. And R polynomial, okay, so the kernel in this case is the R polynomial in the theory of Coxeter group. And geometrically is the, okay, I call it virtual polynomial of the, so this is the Richardson, open Richardson variety, which briefly appeared in Melissa's talk. Thank you, Melissa. I feel like the morning two talks really helped me to prepare my talk. This is the open Richardson. I do the virtual Poincare. So virtual Poincare polynomial is also, I call it virtual Poincare because I want to stick to my notes, is a chi-y genus in Eric's talk. The way I like to think about it is just a point counting polynomial. If it's a torus, I just count how many, okay. I just pretend it's defined over finite field. I ask how many points are there. And as a Q vary, it's a polynomial. Okay, so this is like the point counting polynomial of the Richardson. And okay, now let's double check with Luis. This is correct? Okay, this is
No. So you wrote left KLS equals 1 in all these cases, but it's only true in the last one. In that case, I think it's the Kashan-Lustig polynomial of the same group, but maybe evaluated in -x, I think. So it's not
so it's also K polynomial.
Yeah.
Yeah, I wasn't very sure. When I wrote this, I knew K polynomial of the reverse. I think it's like the Richardson, you are looking at singularity of the reverse Schubert variety. Of maybe okay, reverse. Okay, let's not be too specific. It measures singularity of the Richardson variety. So left and right basically kind of we'll see this later better with our new like interpretation, but it's like really you have two ends and you are measuring the singularity. And how you measure singularity again is the local cohomology, the local intersection cohomology. If your variety is smooth, the intersection cohomology group, local cohomology group is like constant sheaf. There is only 1 in degree 0 and nothing else. But in general, if you have natural singularity, you have more complicated cohomology group. And then here they really like it's not clear what this is.
Geometrically, we have no idea, but combinatorially, we know that it enumerates path in the Bruhat graph according to descents. So there's a combinatory interpretation, let's say.
Okay, and it's a question mark. That is correct. Okay.
Yeah, geometrically we have
the question mark. And then we can go further down the list. If I start with matroid, geometry is realized by hyperplane arrangement. We all should be familiar. And in this case, the kernel is the characteristic polynomial of the matroid. And geometrically is the, okay, again, we see this in Eric's talk, is the chi-y genus of the, okay, Eric mostly talk about the reduced characteristic polynomial, but if you do the non-reduced version, you don't projectivize. You just take the linear arrangement complement, do the point counting or do the virtual Poincare polynomial. That gives you the characteristic polynomial. And then, I hope this is correct. Okay, finally, I got one correct. Left KLS is 1. Right KLS is the KL polynomial of matroid, introduced by Elias Prosford and Wakefield. And it measures the local intersection cohomology group of YA, which is the matroid Schubert, right? Since I'm here, I'm not assuming everyone is familiar with this YA, so let me just tell you what YA is. So A is given by a collection of hyperplane in CD. So I can assume each HI is defined by Li equals 0 inside of CD. And I have n of them. And what I can do, and Li are linear functions. What I can do is I can put all the linear functions together. And YA is defined to be the closure of FCD. And where do I take closure? I take closure in P1 to the n. So coordinate wise, I can multiply by P. So I guess most of you should be familiar, but if you have not seen this before, that's what the Y is. It's called arrangement Schubert variety or matroid Schubert variety. It behaves very similar to Schubert variety, but it's not a Schubert variety. We'll come back to this later, also discuss its geometry. And the motivation of the definition of the Chow polynomial is actually coming from this. The Chow polynomial, so we don't know this, we better know something, otherwise why we define it. So this is the point counting of the virtual polynomial of the wonderful model. Maybe more people may be familiar with the wonderful model, but anyway, let me recall you the definition of what is the wonderful model. So you have hyperplane arrangement. So now you have a vector space, let's call it V, is the image of FCD instead of Cn. Now I'm trying to define. I say this is the wonderful, I guess like everybody knows, but let me anyway, just recall the definition again. I mean, maybe you can define it differently, but let me tell you how I want to think about it in this talk. So then I can take V intersect with C star to the end. Okay. V is a linear subspace in Cn. I restrict it to the torus, and I quotient by the diagonal action. And this will sit in C star to the n. Cn. And this is a Toric variety C star to n minus 1. I can convertify it to the permutation of dimension n minus 1. And XA is defined to be the closure of this. In X. Okay, let's not expose the third board. Any question? Yes.
The G polynomial is just the input is the combinatorial data poset. From that poset, you can just compute it. Or
I need the poset and also I need the coefficient polynomial.
like in the first.
Oh, in the first row? Yeah, so there is a formula. I don't want to write it down. Tells you if you give me the kernel, I can construct the Chow polynomial. So there is a combinatorial formula. And here, if you just give me the poset, give me this polynomial, I can construct it. And it's a theorem of this Lewis and his collaborators that you get a pattern drawing polynomial. And okay, it seems now it's known that there is a Toric variety that give you the this polynomial for polytope. And this is mostly for motivation. If you are familiar with one of the three, I'm happy. I mean, I don't want to get into all the detail or give you a detailed introduction of the theory, but I want to tell you why or what do we want to do this talk. Any other question? Okay, at least part of the goal of this talk is to fill in what this is. I'm not gonna be able to fill in what this is, but I will try. So I will do something by I'm gonna add a new row. So I'm gonna start with the polytope P, and I'm gonna add a new row, and then here I can fill in what this is. But I cannot do it here, so you have to ask Luis to really care about this. That's the motivation of part of the motivation, and another thing we want to do, if you like Schubert variety or Richardson variety, I'm also gonna tell you something about the rational smoothness of the Chow quotient of the Schubert and Richardson varieties. And also using this kind of construction, we can have rational smooth models like residual similarity in some sense of Schubert and Richardson varieties. Okay, we just kind of have this thing recently figured out, but we were also like a week ago aware that Alan Newson has a stronger theorem. For this too, maybe if you want stronger theorems, You should ask Alan. Oh, I hope I didn't spell your name. Too many mistakes already. That he has better answers. So somehow we from very different motivation we can arrive at similar constructions, but Alan used some different method and he can remove the rational, but get smoothness as a stack. Maybe at the end, if I have time, I'll just briefly tell you what's the difference. And the tool of this talk, or the main ingredient, what we are going to use is the BB theory, Bianchi, Brula, not really BB theory, just BB decomposition, if you are familiar. If not, I'm going to tell you. And also Chow quotient. Questions?
For either yours or Alan's results, you're saying you have a resolution singularities of the Richardson,
Yes.
and that's part of the.
It's rationally smooth only, not smooth.
It's actual resolution, not like a bot sample, something like where you actually have a isomorphism onto a dense subset.
Yes.
Okay.
But Bose-Samuelson is.
It's not a strict resolution, if that's your question.
Okay.
So it will blow stuff up that was already smooth.
Yeah, okay, yeah, that's right, that's right. Okay, so let me tell you what is the BB decomposition. Okay, let's start with for a projective varieties. The BB theory originally was for projective variety, but we can also do it for polytope because polytope is essentially Toric variety. That's can be reduced from the BB geometry. So let X be a projective variety with an attribute C section. And for simplicity, let's always assume that the fixed point locus is finite. So there are finite many fixed points. There is no positive dimensional fixed points. And I denote by X. Let's start the figure. Okay, and then given any point, okay, let me call it U in X. So I can define two subsets. The same thing. Okay, let me just say the same thing, except the limit is t equals to infinity. And so the limit at t equals to infinity or t equals to 0, the limit is always the t star fixed points. So that tells you that you have a disjoint union. This is BB decomposition. Here, the same over the same. Said theoretically. Because every point goes to a unique point by the torus section. Okay, and it's also not hard to see that BB plus U and BB minus U, these are all locally closed subvarieties. Okay, let's do some example. Let's do a really easy example, P1, and I think of as C union infinity. And there is a C section just by rescaling C, the most naive one. And there are two fixed points. Okay, so P1 look like this. This is 0, this is infinity. And BB plus, the BB plus decomposition will, okay, so will be defined like this. And you basically ask what x gets collapsed to a point, a fixed point. So if I take 0, you see the whole like middle interval gets collapsed to 0 when t goes to 0. So you get this. And the infinity point. If I look at BB minus, I have a point at 0 and the rest. It's clear? Okay, that's the only example I'm gonna do. And then I'm gonna tell you a fact. If x equals g mod b is a flag variety, and if I take a C star inside of the maximal torus T, which corresponds to a regular dominant weight. Okay, I tried this with both Adam and Mateusz, so I should not make a mistake here. Wait. Then the BB plus give you the Schubert decomposition. The decomposition into Schubert cells. And the BB minus, okay, I hope plus and minus I did myself. The opposite.
You have the way I like it and nobody else does. So well done. The plus and minus are the way I like. I call those the Schuberts and those the opposite Schuberts. So carry on. Okay.
I'm not sure what happened, but okay.
Oh, yeah.
To use a different notation of plus and minus?
Unfortunately, many people do.
I think I'm following the original paper of
No, the question is which is Schubert, which is opposite Schubert.
Ah. Okay, then okay. Let's ignore. There is always like a positive. I mean, okay, there is always
Power of 2.
Okay, or if you want the other way around, or and so we have also seen this is what we talk about. Okay, so let me use U. These are the open region set. There is no ambiguity now. Okay, here we can do one more example, which is not essentially different from the previous one. Is okay. Let's look at P1 plus P1. Okay, now I'm thinking as like a flag or product flag, right? So the P1 cross P1, this is 0, 0. Again, the cis action is the center action on each of the factors. And then the BB plus will look like, okay, generically it's contracted to the origin. So okay, there are four torus fixed points. Generically, it's collapsed to the origin. So this is the open cell, and then you also have this. You also have this, and you also have this. And BB minus is just the opposite picture. And I also have the origin. Okay, let me draw it here. Okay, we should remember this picture because for the matrix Schubert variety, later we kind of will come back to this, even though this is a very simple picture. And you can easily see this will generalize to higher power of P1, and we will kind of see this picture later. Let's remember this.
Are you going to always be in a situation where cells are affine spaces, or
No.
Okay.
Now let's briefly talk about BB decomposition for polytopes. So, okay, a polytope basically a Toric variety. You think what happened for Toric variety in this language and translate to polytopes is so P is a convex polytope, and what's the C section for polytope is just okay. So P is a polytope in Rn, and the additional data for torus section is actually a linear map from Rn to R. And I want to fix point to be isolated. So I want, okay, so let me call LP to be the set of vertices of P. And I need L has distinct values. Let's for simplicity always assume this is the case. And then what is BB plus of a vertex V? So here V is a vertex. This is the relative interior. Okay, is the union of, sorry, it's a union of relative interiors. The relative interior of faces F such that okay, I want the going down, I hit V, so I want the minimum of F is V. And I can define BB minus of V is just the union of relative interiors of the face F such that the maximum of F. Taking minimum of maximum of face is like taking the limit as t goes to infinity, or I mean, take interior point of corresponding torus orbit and push it to infinity or push it to 0.
Maximum with respect to n.
L, yeah, where's L?
Yeah, maximum. I mean, with respect to L. Okay, so yeah, so in theory, like this depends on L, so there is always like a secret L.
And L is this continuous function.
Linear.
Linear.
L is a linear function, yes. And now I'm actually gonna define one more notion. I can also define this for varieties, but let's not do that for varieties. Just for polytopes is I can define a relation. O is a relation on LP, which is defined by O UV if there exists a phase such that the minimum of F, again, minimum with respect to L, the minimum vertex is U, and maximum is V. And geometrically, if I do it for projective varieties, it basically says there is a point in the variety whose, if I push to infinity, I hit V. If I push it to 0, it hits U. That's the relation. Okay, let's do some. Okay, I'm gonna erase this. Let's do some examples. All the examples will be very easy. The first polytope will be just a line segment. And the BB plus will be yes. I think at this point, did I do this? I do this right? The minimum is, yeah, I think.
So L is height on the board.
Yeah, that's right. L is the height for all the examples. Thanks. And I can do a triangle. That's my second example. Again, height is the L. So generically, if I go down, generically I hit this point. So have like an open. So it's a triangle, but without this edge. I don't know how I write that, like
Dashed.
that. Oh, yes, that's a good idea. And if I take a generic point on the removed line, I get this. Okay, this not. And also the top. And I can do it BB minus. Take the point, line, and dashed. And then this point going there, and then the bottom. And it's important. I don't want to think of BB cells are faces. They're really union of interior faces. I want to remember which is in it and which is not. It's important that this edge is not in BB plus. This is like you want to distinguish Schubert cell and Schubert variety. So if you're familiar with Toric variety, I guess probably you are. There is this correspondence between polytopes and the Toric variety and C star action, which correspond the function L, and then the BB decomposition are basically like it's really corresponding to each other. Now, the same our first result to assume. Okay, from now on, I'm always gonna work under this assumption. I assume BB plus U and BB minus U. For all U, they are all irreducible. Okay, so where am I? So now I'm under the assumption that we are working under for a polytope. P is a polytope. When I talk about polytope, from now on, I need to assume that the BB cells are irreducible. By irreducible, I mean the closure is a single phase. It's not two phase. Let me give you an example. I want to exclude this case. So if I take a tetrahedron, of course it's okay. So the bottom, I don't want it to be flat. I want it to be tilted somehow. However it's tilted, it doesn't really matter. But the height function is not constant on any edge. This satisfies the condition. But now imagine if I'm gonna kind of pull this edge a little bit up, I will get this picture. Wait, no. It's another vortex. And you see, B minus of this point, if this is U, not irreducible. Because the B minus is the union of this face and the back face, and nothing else. I mean, okay, the relative interior, there are some sides, but if you take closure, you get two different faces and nothing else. And I want to avoid that. I run into problem, all kinds of problem. I'm not sure whether the result will fail for this, but it just the argument will get really complicated when it happens. So let's assume it doesn't happen. And for most interesting polytopes, this now I can state the first theorem. Assume star. Okay, so assume I already write it, so I'm not right. So for polytopes, for P and L, satisfying star, the following are equivalent. 1, BB plus is a stratification. Second, BB minus is a stratification. Third, O is transitive. And as part of the theorem, okay, the actual theorem has like 7 or 8 statements. They're all equivalent, but I don't want to bore you with too many. I just want to say this is really a natural property. And in this case, so if one of this happens, so equivalently everything happens. O is a gradient set, or O defines. Okay. Many of you look confused. Let me again give you some examples.
Sorry,
So-
what does the phrase in this case refer to here?
In this,
The
okay.
assumption
1, 2,
that
3.
Yeah.
They're equivalent.
If
If one.
if one of them holds, okay,
Yeah.
okay, I see, sorry. Thank you.
So a good example will be a diamond. Again, height is the function. And now, so the poset is just the usual, like the Hessian diagram is just exactly that. And this always transitive because this is bigger than this because there is an interior face, which the bottom is this, top is this. And this face edge defines this is bigger than this. So this is a good example. A bad example is this. This first, let me show you. O is not transitive because this is bigger than this, and this point is bigger than this point. But this point is not bigger than this point because there is not a face whose top is this and bottom is this. And it also fails BB plus is a stratification because when I look at BB, okay, let me see. I want to do BB plus or BB minus. So what is this?
It's vertically symmetric.
Yeah, it's symmetric, but this is a picture I have in mind. So let me see. So this is BB minus. Okay, so what is the definition of being stratification? Stratification says if I take closure of every stratum, it should be a union of strata. So if I take the closure of this, I adjoin this point but not the rest. So it's not a strata. So this is a bad example, or our example where all of them fail.
Sorry, do you want it to be VB plus and do you want that to be a frowny?
Okay.
Oh my God. Like you take the opposite of the whole top. Right.
Okay, non-examples are still good.
Thanks. Most of you are still awake otherwise. But I shouldn't agree to be recorded. I regret. Okay, so now you see kind of, okay, I was hinted there should be an additional row, and I'm filling out the additional row. So the P is the, okay, I need more assumption, but you can see it's gonna be not gonna be the polytope, but like the poset on the vertices. Okay, now, okay, I call this equivalent conditions double star. So a star and double star. Okay. And the second theorem, who is, okay, assume always a star and double star. And also, if BB plus U intersect BB minus V, simple, okay, I'm gonna explain this. For NA, U less than V, actually, I don't have to assume this because if U is not less than, strictly less than V or less than equal to V, this intersection will be empty, but this is also part of the equivalence that I did not tell you. So if this is simple for all of this, okay, I have to explain what simple means. Then K UV T define the sum of Ni, I not 0, T minus I to the T minus 1 to the I power defines a kernel. So poset I already tell you is just the P together with O. Oh, not P, sorry, LP. So the set of vertices together with the graded relation. Okay, first let me tell you what is Ni. Here, Ni is equal to the number of interior faces of this intersection of dimension I. Okay, basically, this is like a union of interior faces, union of interior faces. The intersection is again union of interior faces. And I count how many of them are of each dimension. And this will be Ni, and I sum them up. This will be a kernel. Okay, I'm not gonna write this. I'm also kind of a little bit behind schedule. So this poset, this will be L of P, and with O, this is Toric variety. The kernel will be this. And then let me tell you the Casaluci polynomials. This is the poset. And the right Casaluci study polynomial FUV is equal to G. Okay, it's a little complicated. Star of U bar BB plus of U intersect BB minus. So this is a closure. This will be a face. This will be a face of P, and U is a vertex of this face. And I take the star. And what I really mean is this is a G polynomial. Study is G polynomial. And this is really like a cone. And I'm taking a cross section of the cone that gives me a polytope. And if I take the G polynomial of that polytope, it will define the right. Yes. And if I replace this by V, star V, then this will be the left KLS polynomial. G UV. So you can see this phenomenon that you have left and right really corresponds to whether you look at infinity or you look at 0. Question?
Just can you refresh my memory? So I remember at least somewhat what the G polynomial of polytope is, but then the star is an operator on the G polynomial or on the polytope?
Okay, yeah, sorry. Yeah, the way I write is pretty bad. What do I mean? So I have a face and I have vertex of the face. So I can take the cone of this point of that face and I take a cross section.
Yeah.
That will give me a polytope.
I see.
And that's polytope.
Okay.
So again, it's really like the singularity of the Richardson. Remember? KLS polynomial remembers the Richardson, the singularity of the Richardson. Or Schubert variety. I mean,
why is that a face and not like a union of faces?
because each of them is a face. I assume like actually it's part of the unwritten equivalence relation that you can take closure, the intersect is equal to the intersect, then take closure. Yeah. So if you take closure first, I think it's more evident that you got a face. Yeah.
And what does the simple mean under 0-2?
Yeah. Oh, sorry, I haven't explained this. Okay, so this will take some time and I'm low on time. So let me just say it without writing. So this polytope will not be this. I mean, this is not really a polytope, right? It's a union of interior faces. This polytope may not be simple. What I claim is it has to be simple along the directions where you have the interior face. right? For example, if I take the triangle, still here, the Richardson of the top and bottom, the Richardson is like the Richardson. If I take this and I take the top and bottom Richardson, it's like this: the edge, interior, and the two. And okay, so this should be dotted, dashed. So, for example, okay, this is a too small example. Imagine if I have a bigger example. For example, I allow the polytope to be singular here, but it has to be simple along this. That's what. So it should be really mean like this is part of the Toric variety, and there is or rational. Another question. Okay, now come to the second part of the talk, which is the Chow quotient.
Waited differently.
Okay, I'll try not to run out. And we only consider Chow quotient more general. Let's only consider the case where I have a seesaw action on projective one. Okay. And whenever I have a projective variety with the group action, usually people are being interested in how to define the quotient of the x by the action. But if you just do a naive quotient, it won't give you a good result. So usually what you can do is you can take some open set where the action is kind of nice, and then you over the open set you have a good quotient, and this you somehow compactify it. Okay, what we do is okay. So there will be a good open set where you can take quotient, and the Chow quotient does this. It's a map. So the question how really take quotient is really how to compactify the space. So I'm gonna compactify it in the Chow variety of X. Chow variety parameterize all the cycles of X. It's not a finite type variety, but if you kind of specialize to the topological type of the cycle, and in this case we will, it's the immutable line of a finite type variety. And the map is so the point here, the quotient here corresponds to orbit, seesaw and I-seesaw orbits. I send it to the closure, to the class of the closure of the orbit. And then I take closure there. So the Chow quotient okay, I denote it by a triple slash. This is defined to be the closure of in the Chow variety. Definition may be abstract if you're not familiar with the Chow variety. Let me just give you an example, two examples. I hope this will kind of explain the geometry of the Chow quotient. So let's again take my favorite example, P1 cross P1. And again, the standard C-section, which just scale each vector. The picture looks like this, P1 cross P1. So this is X. X now will be like C-star square, where I really have this is like interior square, where I have a good quotient. So if I take an interior point, the C-star orbit will be like this. And the X is not to my C-star, this is just C-star. And the point is when I take closure in the Chow variety, I really kind of try to understand how the cycle degenerate as I take closure or I degenerate to the boundary. So this curve, when it degenerates to the boundary, you can imagine it breaks into two curves. And the homology class didn't change, right? The yellow and blue, they represent the same homology class, one of them. So the Chow quotient will be, the C-star gives me, the C-star is the good quotient, and I'm adding a blue point to correspond to this, and I'm adding a red point corresponding to this. So the Chow quotient of P1 cross P1 is just P1. Well, it's too small dimension, nothing interesting happens. Let me try to squeeze in here. What if I do P1 cross P1 cross P1? 3 copies. Now I have a cube. 0, 0, 0, infinity. Again, the interior will be like C star cube. So in the interior, I have a point like this. A point in the Chow quotient will correspond to this one cycle. It's its orbit. But now this orbit can degenerate in many new ways, more interesting ways. For example, I can degenerate to this. This will be like a special point of the Chow quotient. And I can also degenerate to this. This is also a very special point. And there are less special points, the orange, which is this. Okay, I mean, it's a kind of straight curve, and then go there. The orange corresponds to a one-dimensional family. I have the freedom to vary on this square, but not here. So the total Chow quotient is two-dimensional. The interior is C star square, and I have 6 special points. I have a red, I have a blue, I have a red, and I have 4 more. So let me draw them like this. And then the orange becomes a line like this, a P1. I mean, the interior of a P1. So if you join the orange with the red and blue, you get a P1. So this is a familiar picture. This is the permutation, the two-dimensional permutation. And the claim is, well, this actually the Chow quotient for Toric varieties are very well studied and understood by Kapranov, Sturmfels and Zelevinsky. And that really. So if I take P1 to the n, this is the n-1 dimensional point. And now I'm going to tell you a magic, which is we know why A sits in here. And now what do you say I get? So remember, what's this in the permutation? Xn. This fact actually follows from this fact. Because on the open part, I know this was same. This is just the quotient of the hyperplane arrangement complement. And I'm taking closure in here. Okay, now you see. Another way to think of this is just I take the Chow quotient. So now let me, okay, I'm really short on time, so let me not write theorems anymore. Let me just tell you, if I want to fill in here, this will be the Chow quotient of the Richardson variety. Okay, this is the Richardson variety or XU intersect XV. Quotient. Okay, it's an analogy. There's something to prove, but really, the magic is the Chow quotient has a very interesting stratification, depending on how this curve breaks. This is like again Renzo's talk yesterday. So curve can break. How it break gives the stratification of the Chow quotient, and using the stratification we can check it gives the, and also the virtual boundary polynomial is like additive for sub-varieties, and we can really check this does give the right the formula for Chow. And then if I add the middle row, this will be the vertex, this will be the LP with the relation O, and this is XP. This will be, okay, I told you there is a complicated formula for the kernel. These are the G polynomials of the cones. So here is again the Chow quotient. I mean, if you start with polynomial, there is a combinatorial notion to do this. Without, you don't have to require the P to be rational. There is a notion to do this, and You just put it there. Can I have two more minutes? To tell you this statement about smoothness. So you have a variety whose virtual polynomial is palindromic. Remember the Lewis theory tell you the Chow polynomial is always palindromic. Then this will make you wonder, you have a variety whose, like if you start with Schubert variety, the virtual polynomial is just you count the number of elements in the Bruhat interval. In general, it will not be palindromic. Usually, if you start with a smooth variety, smooth projective variety, because of polynomial duality, you have palindromicity. So then you wonder why this has palindromic polynomial. The answer is the Chow quotients of the Richardson variety. If you do Chow quotient, it's rationally smooth. And you may not like this because you do Chow quotient, you can kind of destroy the variety. You see, XA, YA becomes XA, you kind of destroy the variety a lot. What if you don't want to destroy the variety? What you can do is you take P1 cross XUV, then quotient by C star, the Chow quotient. You increase dimension by 1, Chow quotient decrease dimension by 1. I claim there is a birational map to XUV, and this is rationally smooth. So in this way, you can get a rational smooth model. And let me, I think I can, this will be the last sentence. So how do I construct this map? So here, element corresponds to a cycle, one cycle gamma. I just send it to gamma, intersect with, I can choose anything in C star, which I choose 1 cross XU. And I consider this as a point in XU. So what happened is, this is XUV, this is P1, this is the bottom, this is the top. A general curve look like this, a special curve look like this. It breaks. But because I know this direction degree is 1, so I know it intersects the horizontal line has to intersect at exactly 1 point. And that is the point I define the map. And this will give a rational smooth model of a Richardson. And Alan says this is not how you should think of it. You should think of it, instead of using cycles, you should think of it as stable maps from curves to Richardson variety. And if you study deformation theory, you don't want to deform cycles, you want to deform maps. That's the reason he can get a stronger result. Okay, thank you.
We have time for 1 or 2 questions?
Yes.
I was curious about these posets you get data. So to what extent do they look like Bruhat order? So like in Bruhat order, the rank 2 intervals are always diamonds, the rank 3 intervals are always K crown. Can you say something about these posets?
Yeah, so rank 2 poset is either triangle or diamond. Rank 3 poset, I don't know, but I think there should be finite many type. It should be, yeah, I would guess this. Yeah, I cannot say more.
In Bruhat order is actually K crown. I mean, you can arbitrary Coxeter group have an arbitrary size K crown.
Yes, but for polytopes, this is what I can say.
Yes.
In general, I mean, I guess we get the same poset in the Coxeter case.
Okay.
So the only new poset we get is like the polytope with the linear function. And I think rank 2, there are only 2 types.
You do this P1 trick for the matroid setting, what happens?
Oh, you get this bi-augmented one. That's a good question. You do augmented model, you blow up everything at infinity, but you also blow up everything at 0. So you blow up, I call this like bi-augmented.
Is it not a wonderful variety of like M direct sum you want to know?
It is, yes, it is. Yes, it is. P1 is exactly what.
So in the examples, should we think about genus 0, degree 1 maps to a product of P1?
When you have a Richardson or like a flag variety, degree 1 doesn't really make sense. You kind of, so what, I don't think degree 1 really, probably not degree 1. It depends on the Caesar action. You can actually take a very random like dominant weight. And the Caesar can be kind of complicated. And you could, for example, P1, if I take just P1 plus P1, I don't have to do 1, 1. I could do 97 times 1, 1. So Caesar them with this weight. The theory still works. You can still do the Chow quotient. Then you are parameterizing. If in Allen's theory, you will be doing stable maps of from P1 to this with this degree, which is totally fine.
But there's the question of the weight that you're talking about now, or co-weight really. The co-weight you're talking about now, function versus the degree in XUV. So
yeah, but the degree can also be high, right? If you take this random.
But so the point is, of course, you take first you fix your circle action. You use that to figure out what degree you want.
Okay.
And then you take that, but with as you say, 1 on the P1. So you definitely want 1 on the P1 so that you get this real line trick. But it should be 1, comma, and then the degree of a general orbit closure.
The graph space.
Yeah, the graph space.
Yeah, so you kind of know the class as it is. Usually like the way I think of things are like you don't really say the degree, but you say the homology class. Maybe that's a better way.
I mean, I'm using the word degree, but I mean curve class. I mean,
Okay, degree is curve class.
An element in.
Yeah, it's not a number, it's really a class. Yes. That's the general orbit. Yes.
Whenever you want to do a Chow quotient, is it always replaceable by what the stable maps do, or is it like some theory Chow quotient is better?
It depends on what you want. If you are purely from a combinatorial point of view, without worrying about singularity, I find Chow quotient better. Because for example, Toric variety, I think the Chow quotient is very well understood. But if you start with singular Toric variety, the stable map may be complicated, I would say. So it depends on what's your motivation. Yeah. And also Chow quotient is easier, I think, to instead of like stable maps. Stable map is some more fancier, and they give you a stack. Chow quotient give you a variety.
All right, we'll save further questions for the break. Thank you.